Welcome to this explainer, everyone. If you're stepping into the world of telecom room or equipment room design, consider this your official apprenticeship masterclass. Today, I'm going to walk you through a hands-on transformation of how we engineer our physical spaces. We're talking about finally moving away from that manual, error-prone scratchpad math. The kind that inevitably leads to tripped breakers and totally blown coordination budgets, and stepping into the world of precise, standardized engineering handoffs. We'll be working directly with PLEX version 2.25, the Power Load Examiner. I've literally used this exact tool on federal, healthcare, and massive coordination sets to ensure our limited energy infrastructure actually functions the exact way it's supposed to when the power finally flips on. So grab a coffee and let's get you up to speed.
Here is our exact syllabus for today. We'll start with establishing our TR and ER design baseline, then cover power factor and UPS sizing, and tackle real draw and POE budgets. After that, we'll break down wall devices, jump into generator sizing and NEC rules, and finally look at our ultimate goal, the engineering handoff document. Basically, we're going to build a room from the rack up.
All right, Section 1, TR and ER Design Baseline, Building the Foundation. Let's get into it. Okay, let's dive into this. For years, we limited energy designers have relied on incredibly disconnected spreadsheets or, honestly, just wild mental math to size a room. But here's the reality. Before you can specify a UPS or tell the mechanical engineer how much cooling they need, you absolutely have to know your exact load. Guessing? Well, guessing leads to blown budgets and overloaded circuits. We need to abandon those messy spreadsheets for actual preliminary engineering. To solve this, we use PLEX. Notice how it's a fully browser-based workspace. This is absolutely crucial, especially for sensitive projects like federal or correctional facilities, because no data ever leaves your machine. The whole shebang is client-side. And as you add devices, your total watts, heat load, generator sizing, and rack fill update instantly. It's like having a live, real-time pulse of your room's physical reality.
But before we go dropping our first server into the rack, we really need to establish our professional boundaries. Here is our absolute golden rule. The tool handles the sizing math. The EE stamps the work. You see, PLEX was built by an RCDD to calculate preliminary loads for coordination. Our job is to give the licensed electrical engineer rock-solid, accurate numbers so they can actually design the electrical system. We provide the accurate preliminary loads. We do not do the final electrical design. Never cross that line, okay?
Moving right along to Section 2, Power Factor and UPS Sizing, Sizing to Reality.
Now that we've set our boundaries, this brings us to the first major trap in limited energy design. It's the total misunderstanding of heat load versus UPS capacity. Honestly, this is where most junior designers make their first critical mistake. On one side of the coin, we have watts. Watts represent real power, the actual energy that does work and generates heat. The mechanical or HVAC engineer needs watts to calculate their BTUs for cooling. On the flip side, we have voltamps or VA. This is the apparent power. It's what the utility actually delivers to the room and what your uninterruptible power supply must be sized to handle. The electrical engineer needs VA. Listen, if you size your UPS using only watts, you are going to undersize it. Guaranteed. No way around it.
Now, what's really interesting about this slide is how it defines power factor. Power factor is simply the ratio of real power to apparent power. PLEX is smart, so it uses a very conservative design default of 0.90 for mixed telecom loads. Let's put that into perspective. If you have a 500-watt server, you don't just need 500 VA of UPS capacity. You take that 500 and divide it by 0.90, which means that server actually draws 556 VA from your UPS and your circuit. That invisible 56 VA difference, yeah, that is exactly what trips breakers if you aren't running the math correctly.
All right, Section 3. Real draw and POE budgets, tracking actual watts. With our baseline power physics understood, let's actually start populating the rack infrastructure and protecting our power over Ethernet headroom. We need to put some real equipment into our digital room. Inside the tool, you've got this great device library dropdown. Instead of hunting down manufacturer spec sheets at 2 in the morning for every single item, you just select from dozens of presets. You can literally just drop in a Genetic StreamVault SV500 server, a Cisco CBS350 PoE switch, or an APC Smart UPS straight into your active rack. And it's pretty slick. When you drop the UPS in, PLEX relisters both its load, because it draws power itself, and its capacity to protect the other devices. It's doing all that heavy lifting for you.
And this brilliantly illustrates how we handle power over Ethernet. Say you have a Cisco CBS350 48-port switch with a 370-watt PoE budget.
A massive mistake people make is sizing their load based on the maximum PoE class limits. We don't do that. We size based on the real draw, meaning what the camera actually uses in normal operation. For example, an Access Q61 PTZ with a heater running might pull a real draw of 60 watts, but an indoor Access P32 dome, that's only drawn about 8 watts. If you assume maximum class limits for every single port, you're going to falsely overload your system on paper. By tracking real operating watts, PLEX gives you an incredibly accurate picture of your actual PoE headroom.
Let's jump to Section 4, Wall Devices and Access Control, Independent Circuits.
Let's shift our focus away from the rack for a minute to explain how we handle field components and access control system power. Because, let's face it, not everything plugs into a neat little rack PDU. This is a vital distinction in PLEX. Your wall and field devices, we're talking about things like a Mercury LP1502 controller, a life safety EA power supply, or your electrified door hardware, they all require separate circuit math. They're independently mounted and require their very own dedicated circuits directly from the electrical panel. PLEX calculates the amperage and recommends independent breakers for every single one of these field devices, making sure you, the access control coordinator, and the electrical engineer are perfectly synced up.
Which brings us to Section 5, Generator Sizing and NEC Rules, the Law of Continuous Load.
So, the crucial point is, we aren't just doing basic arithmetic here, we are engineering to code. 125%, that number is literally everything. The National Electrical Code, or the NEC, dictates that circuits and generators feeding continuous loads, and that means anything expected to be energized for 3 or more hours, which is basically all of our telecom equipment, must be sized at 125% of the actual load. PLEX automatically enforces this standard right across its circuit and generator sizing outputs, so you're always compliant.
Here's the exact progression the tool uses to spit out a kilowatt recommendation for your backup generator. First, it calculates the base load of every single server, switch, and camera you've added. Second, it applies that NEC 125% continuous factor to get your minimum legal size. Third, it generates kilowatt recommendations that include a 25% or 50% growth margin. Because, as a good engineer, you never design a generator to be maxed out on day 1, you always design for day 2 and beyond.
And finally, Section 6, the Engineering Handoff Document, Delivering the Math.
Now we arrive at the final stage of our workflow, generating the actual coordination deliverables you're going to bring to the design meeting. PLEX produces a beautifully structured summary formatted right for PDF export. Look at how it aligns all that data we just worked on. For the electrical engineer, it hands over watts, amps, and the NEC-compliant breaker size for both the rack and those individual wall circuits. For the mechanical engineer, it translates those watts directly into BTU per hour and cooling tons, explicitly tacking on a 25% thermal buffer. You see, you aren't just handing them a messy list of parts. You are handing them the exact, precise metrics their specific disciplines require to do their jobs right.
But hey, reality check. As your mentor here, I need you to remember our scope. This document is a preliminary coordination tool. It is absolutely out of scope for us to provide final electrical design, detailed battery string math, conduit fill derating, or one-line diagrams. We provide the precise calculated sizing inputs. The licensed engineer takes those inputs and designs the actual electrical system. Staying in our lane is exactly what makes us trusted professionals in the room.
So I want to leave you with this final thought before your next project kicks off. Are you still going to be guessing your loads with scratchpad math, crossing your fingers, and hoping the breakers don't trip when the system goes live? Or are you ready to use a standardized, accurate tool to actually engineer them? Take everything you've learned today, apply it to your next coordination set, and just watch how much smoother your entire design process becomes. Thanks so much for joining me on this explainer. Keep learning out there, and keep engineering.